Hello, everyone. Welcome to ACS Webinars, where we work to connect you with the best and brightest minds in chemistry, live every Thursday from Washington, D.C. I'm Michael David, and I'll be your host for today's broadcast, which is being co-produced with ACS External Affairs and Communications, the American Physical Society, and the Materials Research Society. Now, if you were to ask the general public about how we use helium, they might not be able to think of much more than birthday balloons. But to those more educated on the subject, they know that it is required to do so much more than that, and that the supply is limited. Sophia Hayes, who is a professor in the Department of Chemistry and a solid-state NMR and low-temperature researcher at Washington University, and Bill Halperin, the Orrington Lund Professor of Physics at Northwestern University, are going to share why helium is such a unique element and how it can be better conserved in the face of a limited supply. Our moderator for today is Will Hartwig, who is currently a Science Policy Fellow here at the American Chemical Society, and who also served as an ACS Congressional Fellow prior to that. He earned his PhD in Organic Chemistry at the University of Colorado Boulder back in 2015. And with that, I'm going to turn it over to Will to get our presentation started today.
Thank you, Michael. Today we will be discussing how helium is found, extracted, and used, why the price and availability can change rapidly, and how those changings are impacting researchers. Finally, we will also discuss ways researchers can conserve their helium, helping preserve a non-renewable resource and saving research funds at the same time, and what else you, the listener, can do to help. Now for our opening speaker, Professor Hayes.
Well, thank you, Will. We're really delighted to be able to come and speak about helium, this irreplaceable resource, and why we think it's important to conserve it. So why are we here today? Why have a call? First, it's important to talk about the helium supply, what we're experiencing now and what we might expect in the future.
And the price is fluctuating. It goes up and down in time. It's difficult to predict, and it varies substantially across the nation.
So the question really is, what can we do? Now, first, the early warnings of a helium shortage to the general public. Many of us know that there's something going on because balloon purveyors, Party City, place like that provide helium balloons for parties, even on their websites will announce that there's a global helium shortage. But there are early warning signs amongst scientists. So for example, this is a quote from AMMRL, a listserv that I belong to, an association of professionals that all deal with equipment that use helium. And so we'll get messages that come across the listserv that say, hey, are you guys getting helium? Our vendor just delayed all shipments. So when you think about helium, there are a number of end uses, and I'm showing a pie chart from a report that's linked at the bottom. I'll point you to the small wedge that's in red, the science and engineering section. This is the statistics from 2015, and we use about 6% in research aims for these helium end uses. Of course, in this pie, there are many other ones. Notice MRIs taking 20% of the supply, things like lifting at 14%. So there's many different uses. You can categorize these in this sort of graphic image from gaseous helium applications, things like party balloons, or even scientific weather balloons, blimps, and the like, all the way to the liquid form, where you see at the bottom corner, things like NMR, MRI imaging, dilution fridges, but even used in the Hadron Collider. So it's got many different varieties of industries that it touches on and research aims. And you'll notice things that might be a little bit unexpected. It's used in the production of optical fibers and semiconductors, and in things like heliox diving, going into deep sea depths. So helium is necessary for everything we're showing on this page. Well, I'm going to turn it over to you, Mike.
So we have a question for all of you, and where do all these vendors get their helium? All right, it was kind of a runaway on this one. 81% said if they got it from natural gas mining, and 52% said from the National Helium Reserve. The next highest was 23%. So with that, I will turn it back over to you, Sophia.
Well, you know, I'm delighted to see how informed the group is that's on this call, because actually that is correct. The two main places that we get our helium are from extraction through natural gas mining, and also where we obtain ours from in the US is from the National Helium Reserve. So it's refined from natural gases, that's meaning methane, CO2, et cetera, at a concentration of typically 1 to 3%. But it's also stored and returned to us from the National Helium Reserve, but that's slated for closure in 2021.
So let's have a little background on helium. Helium comes from the radioactive decay of uranium and thorium. These elements emit alpha particles. An alpha particle is the nucleus of a helium atom. Unfortunately, this decay has a half-life of hundreds of millions of years. So you can see the alpha particle schematically disappearing off there to the right. And how does it stay with us? It gets trapped in the Earth. So we find that helium, which is mixed with natural gases in reservoirs. It's mined mainly for the purpose of extracting the natural gas, and then it's refined to produce the helium. It requires usually about 2% or so to make it commercially worthwhile to separate it from the natural gas. It does appear, of course, in the atmosphere, but only at 5 parts per million, and extraction would be far too expensive. The main sources of helium, the 3 highest producers, are in the United States, Qatar, and Algeria. And for the supplies in the US, mainly concentrated in the area shown by this purple boot on the right-hand side, which is an indication of the location of the major gas fields, the gas fields of natural gas from which helium can be refined. You'll see also an orange line which indicates a pipeline which joins some of the major gas fields together, leading down to the Cliffside field near Amarillo, Texas, where the Bureau of Land Management facilities are located. This pipeline, the Cliffside field, and the Bush Dome underneath it, which is a geologic reservoir where helium can be stored, are all part of what we call the National Helium Reserve. So what causes the supply shocks and the price changes? Across the world, these are subject to political instability, maintenance of the pipeline in the United States, market fluctuations of the natural gas, which can directly influence the price of helium, the natural gas wells that supply a sufficient concentration of helium can become depleted. And then there are discovery of new sources. Most importantly, in 2021, there is scheduled by legislation a shutdown of the helium reserve, which has provided for a long period of time 30% of the world's supply. So that will be a very important issue that confronts us. Now, the users of helium can be thought of in 2 different categories affected by supply and price. On the left-hand side, I show that low-temperature research in physics, chemistry, and engineering, which are on fixed federal grants, which aren't changing so rapidly, are subject to concerns about fluctuations in price of helium. Astrophysics, accelerators, cryogenic detectors are all activities which employ helium to a significant extent. Material science, quantum information research, and cryogenic instrumentation. And on the other side of the panel here, there are end users who have an absolutely critical cryogenic need for helium, specifically superconducting magnets. Nuclear magnetic resonance, nearly all American Chemical Society accredited chemistry departments have on their agenda the important use of liquid helium, and a steady use is extremely important. NMR researchers in chemistry, physics, and engineering, mass spectrometry, these all have critical applications that require liquid helium.
So let me chime in with some stories from the front lines of researchers, because this is some of the community that raises this issue for us. There was a tremendous and compelling story that many of you may have seen in CNN News, where with the power outage in Puerto Rico after Hurricane Maria, researchers there were trying to sustain a very valuable and important superconducting magnet that was used for NMR research. And in the expansion of this photo, you can see that they're using a backhoe to lift a dewar up onto the 2nd story because there was no other way to get these cryogenic fluids into their magnets. And it was a heroic effort. And it just shows you the extent to which researchers will go to sustain this important piece of equipment that's so necessary to the livelihoods of themselves and their departments, their professional livelihoods, that is. So we often find out that there's a helium supply problem through these organizations, as I said, like AMMRL, and there are anecdotes from around the country. Let me give you a sense of this in people's own words by quoting a couple of things that were sent to me. We were scheduled to move our NMR system into our new building. We were told by the vendor we needed 400 liters of liquid helium on hand, but our vendor couldn't provide that much. Our stockroom director did a lot of hunting around, but there was not a single helium supplier in the country that could provide that much. The delay caused us to lose our window. We lost the use of the instrument at a time when we needed it for teaching and research, and lack of helium was the only reason we could not move the instrument on schedule. Here's another testimonial. In October, we were told that we had reached our allocation and no helium would be available for at least 6 to 8 weeks. We have a 900 megahertz NMR instrument that needs 250 liters every 4 weeks, and we went 10 weeks without helium and have never quite got back to a complete fill. More importantly, our helium cost went up 47% at just that time, and our costs for the 900 alone are now $56,000 a year, and that cost has to be passed on to our users. These are just 2 testimonials of many that we receive on this listserv when we track these crises that have come our way. And it's not just supply, it's also the price over time. This is a representative graphic. The citation is shown at the bottom. It was from a report we'll show at the end, and I'll direct your attention to the red line. You'll notice that the helium price over a period of just a short time from about 2009 until 2015 went up dramatically, 400% or so, 350%. And in such a short space on fixed budgets, it's almost impossible to absorb that kind of cost increase if you're a researcher. Helium pricing is also really confusing. This graphic is an interesting one from that same report. Notice that along the y-axis is the liquid helium price, and along the x-axis it's a histogram style plot of different regions of the country. The different colors of dots indicate the level of helium used, from under 1,000 liters to over 10,000. And what it shows is there's no correlation really between price, amount being delivered, and region of the country. So it simply shows that this is a very odd market for this important commodity chemical. So with that, I do believe we have another audience question, and I'm going to pass it over to you, Mike.
All right, we just quickly wanted to poll all of you in the audience. Have you ever experienced a helium delay? Have you never had a delay? B, had 1 or more delays lasting up to 2 weeks. Third, have a delay lasting longer than 2 weeks. Or finally, it's not applicable, you don't order or use helium. %, said they had 1 or more delays lasting up to 2 weeks. 12 said they had longer than 2 weeks, and 14% said they had never had a delay. So with that, Sophia, I'll turn it back over to you.
Yeah, those numbers are very interesting and informative for us to hear, to sort of see what kinds of delays might be built into the system and what people are living with at the moment. And so sharing that data is important for people like me.
So what can we do? Helium conservation and recycling is one way to go. I have here 4 bullets: liquefaction, conservation, and storage, and possibly new directions. Let's talk about liquefaction. There are 4 basic areas of everything from national laboratory large-scale liquefaction to very small single instrument, say less than 5,000 liters per year research. I'm going to discuss mid-scale and small scale. That is, mid-scale being universities that use between 30,000 and 50,000 liquid liters per year, and small scale, which might be a few laboratories teamed up between 5,000 and 30,000 liters per year. Also, you could think that we should conserve our helium, and in some sense, improved efficiency will reduce costs, that's for sure. Part of the conservation might be to store helium. However, helium will escape from the Earth and go into outer space on a time scale which is approximately on average every 2 weeks, so on a 2-week time scale. So storage of gas will really require large volumes, such as the National Helium Reserve. The reserve will be at 3 billion cubic feet in 2021, where it will be privatized. And another direction would be helium-free systems, which could be integrated into single instruments or magnets. The mid-scale helium liquefaction approach has pluses and minuses. For the plus side, it's possible to have a local inventory between 4,000 and 6,000 liters, which means you can weather the variations from short-term non-availability of helium. It would require technical support, which could be an advantage, and it supplies immediately to the users at the institution between 40 and 50 liters per hour. There's a bit of a pricing advantage for make-up helium. That is to say, if delivery is in large dewars and it's delivered to a single site, pricing can be more reasonable. And there's also a bit of a pricing advantage for helium, which is provided by an in-kind program of the Bureau of Land Management, which produces possibly some savings for large users. On the minus side, the capitalization is quite significant, 2 to 3 million typically for such a facility. The cost of a full-time technician must be supported, and there's a requirement for institutional space. As always, efficient helium transfers are essential to reduce the losses from the use of helium in any recovery system. There's also a threshold of 7,500 liters per year in order to qualify for in-kind helium for those federal grants which are reach that level. And here's an example of such a helium liquefier facility. Look at the central panel. This is the liquefier itself. It can produce 40 to 50 liters per hour. On the left side, you can see large dewars. The largest one is the liquefaction dewar. It can hold 1,500 liquid liters, and the technician is ready to transfer 250 liters of helium, which was recovered, which was taken from a provider to make up the losses. And on the right-hand side of this panel, at the bottom, you can see the compressors which are needed to compress the gaseous helium that's returned to the facility and store them in large tanks. Now, on the small scale side, there are pluses and minuses. The capitalization is rather much cheaper, $150, say, to $250,000. No technician would be required. Lab space is required at some modest level, say 300 to 500 square feet. And here, the immediate availability of liquid helium is between 20 and 40 liters per day. It's a very efficient and low-cost approach. On the minus side, the amount of inventory is necessarily quite small, 150 to 250 equivalent liter capacity. This means that fluctuations in price can't be weathered by storage. The lab staff who do the work will have to be from students or postdocs or researchers who are members of the different laboratories, and there's perhaps uncertain availability and cost for the makeup helium, which could be as low as 300 liters per year, can be quite expensive in power, and as always, efficient handling of helium is a necessity. Now here's an example from the University of Alberta of such a facility. On the left-hand side, you can see 175 liter dewars, and on the top of them, you can see a plant. This plant is a pulse tube reliquefier connected directly to the instruments through the gas bag and has helium that's pressurized in the yellow tanks that you can see at the bottom. The facility at the University of Alberta is one that involves 3 different laboratories, all tethered together in a local reliquefaction capability. And here you can see the necessity for storing liquid helium, say in 100-liter dewars, are set up to recover the helium, each and every one of them, into the system that will then store it at higher pressure and then reliquefy it. As always, efficient helium transfers are essential. Don't waste a drop, not even a puff. Let me turn this over to Mike.
So our last question for all of you is, which of these is the highest priority? It would be to refrain from buying helium balloons, improve transfer efficiency, call your Congress member and request a hearing on helium, or all of the above. Majority at 62% said all of the above, 11% said call your Congress member, 21% said improve transfer efficiency, and 6% said refrain from buying helium balloons. So that, Bill, I'll turn it back over to you.
Thanks, Mike. Well, helium for balloons, it's really too small, and it's always wise to improve efficiency. However, it's a higher priority to press Congress to take action, beginning with holding a hearing on ensuring helium supplies for research. And this could be a very important factor in maintaining access to the 3 billion cubic feet, which will remain in the helium reserve when it closes in about 1.5 years. This activity will require congressional action.
So part of the reason we're having this call is because we've been seeing helium supply shocks with increasing frequency. And so because of that, we're always readying for the next one. First is to say there's different kinds or different types of users, some with a fixed periodic need, and in other words, ways to think about what are the most critical helium needs at this point and within the science and research community. We've suggested triaging helium orders, and it's something we've begun to do at Washington University, where we categorize our helium into those instruments that will become damaged or the superconductivity can be lost by not being remaining at very low temperatures. So those critical applications are in a certain category. But there's other researchers like myself that choose to use helium to cool down experiments, and I might choose to avoid that research for some amount of time during the next helium shock. And then there are other optional uses for that helium that might come through. So the triaging system is only to set what the bottom level of demand might be for an individual site, and knowing those numbers lets us plan for the future. In addition, I'd encourage those of you who buy helium now to get engaged in some type of early warning system, maybe with one of your professional societies. And for that, and for those of us that are in NMR, that's the AMMRL, and there might be others through other professional societies. Please do keep officials informed just to build awareness of this need amongst our community. And again, as Bill eloquently said, please call your members of Congress because this is an issue that affects us all and even beyond the research community. So if you want more information, it turns out that our professional societies like the American Chemical Society, the American Physical Society, and the MRS, Materials Research Society, all have policy groups that have been watching this issue actively. They have websites devoted to it. And actually, we got together as a group and produced a report some years ago. We'll provide the link here for you, and that is filled with useful information and other links to things and useful resources for those of you that this affects. Beyond the research community, we also have the federal government Bureau of Land Management website. And while this text looks very small, I'm highlighting with red shapes 2 areas of this homepage where there is useful information on helium that's available for all. People beyond the research community may be interested in the helium facts and figures and to know a little bit more about this critical element. Finally, I'll say that our national academies produced reports on this in the past. There was a recent lengthy report in 2010 that is listed here. It was updated by testimony in 2013 as we were seeing the looming shutdown of the helium reserve and trying to talk about strategies to deal with that. And all of this was predated by a 2000 report that was studying what would happen, the implications of selling off the federal helium reserve after some acts in the 1990s to shut it down by Congress. Bill and I would like to leave you with some final thoughts. And this comes from us, but also from our professional societies listed at the top. And so they've helped us craft a couple of ideas to leave you with some potential points. The first is our administration has listed helium in its critical minerals list last year and has yet to take action on that designation. Number 2, in the short term, researchers that are in dire situations need some kind of assistance and need someone to turn to. Number 3, this privatization, or we'll call it sale of the helium reserve, should be contingent, we feel, upon a continuation of what's called the in-kind program, which provides access to helium for federal users, federal researchers, so to speak. Finally, in the long term, Congress needs to assist federally funded research with helium recycling equipment and development of helium-free technologies. Congress could use monies from the helium royalty contracts for this purpose.
So we have a lot of questions, as you can imagine. I thought we'd start off with some about liquefaction. Perhaps Professor Halperin can discuss a little bit more about, are there significant safety aspects to maintaining liquefaction facilities on site?
Nice question. The most important safety issue is that the storage of helium will require relatively high pressure of the order of 2,200 pounds per square inch, for example. As with handling any high pressure gas, be it helium or anything else, there is a lot of energy stored, and that must be maintained in a careful situation. It is also true that liquid helium evaporate very readily, and if the vacuum that around the vessel and the dewar breaks, then that could be a safety hazard and needs to be monitored. Currently, dewars that hold liquid helium have built-in safety features which make that not a very dangerous situation.
Great, thank you. Could you discuss a little bit more? I don't know, this could go to Professor Hayes or Professor Halperin. About how much liquid helium does a user have to make reclamation viable economically at different levels? I know that the systems cost different amounts, but could you comment a bit more on that? We have a question from Thomas about that.
It can vary from very small scale to very large scale. It's possible to have a plant which is affixed to a single instrument such that the helium that is necessary to use in that instrument boils off, and there is a pulse tube reliquefier which immediately liquefies within the instrument, and that could be at the level of 5 or 10 liters a day. So that's on the really small scale. That's the smallest scale. I would call that a dribbler, where the liquid helium reliquefies and then dribbles down to where it's required to maintain the temperature of 4 degrees. And then all the way up to very large scale.
Okay. So we had some questions about other potential sources of helium. So Michael was wondering that Russia has huge natural gas reserves. He was curious if they produce helium. And we also had questions about the potential sources of helium in Tanzania. So could you discuss a little bit, Professor Hayes, about alternative sources other than the 3 largest countries that were mentioned in the webinar?
Yeah, I'm definitely happy to do that. Russia is reportedly coming online with a new helium source in 2021. And so, of course, we are all anxiously awaiting its coming into the overall picture. It will certainly have an effect on supply and price. Again, as a strategic reserve that's necessary for both industry and research, we might want to consider whether we want to be tied to a foreign supply of an important commodity chemical. That's the first. Tanzania is a very exciting prospect, partly because the helium that was found there was in an unexpected spot. It's in a geologic formation where there was volcanic and crustal movement activity. My understanding is it is not present in a natural gas kind of formation, and so that has both opportunities and challenges. The first one is that we have a lot of technology to separate helium from other natural gas streams, and so we have membranes designed for that purpose. Here in Tanzania, I'm unaware of the entire gas mixture, but if it's not tied up with natural gas, it's likely that there are other acidic gases present that may not be amenable with current membrane technology. The fact is, I don't have enough information to comment on that. But there's also the difficulty of extracting in this very remote part of the world, and also developing the technology to do so, deploying it down there, and finding out what the conditions are. So I think that Tanzania is enticing because it means that maybe we're not running out entirely at the moment. So yes, there are other exciting findings on the helium front, but we may still want to maintain a domestic supply.
Thank you, Professor Hayes. Stephen was also curious if there are other ways to try and reclaim helium once it's been released into the atmosphere, like other gases that we've tried that with. Would Professor Halperin like to discuss that just a little bit, maybe?
My understanding is that it's not commercial. That is, I believe the study that was done in year 2000 that was supported by the National Academy of Sciences made an attempt to estimate what the cost might be to recover helium from the atmosphere, and that it was on the order of 100 times more expensive than what was being projected from the use of helium in the near future. That was back in 2000. So I think that's not viable.
Thank you. So we had several questions about using potential other gases potentially. Hannah was wondering if it would be able to replace helium with one of the other noble gases, perhaps argon, for NMR instruments and other cryogenic applications. So would you guys like to discuss just the potential of using other gases and why that may or may not be a good solution long term?
I think we can both agree that the cryogenic temperatures for superconductivity in materials that are used for superconducting magnets require temperatures on the order of 4 Kelvin, and other gases do not easily reach that temperature level without extra work, let's say, involved. So no, there isn't a substitute for it in that cryogenic realm that I know of.
Okay, that actually leads into the next series of questions. We had several people ask about what the status is for high temperature superconductors. So would you like to discuss why that is or isn't very practical also long term, potentially?
Well, let me say a word about that. Even the magnets that are constructed from high temperature superconducting materials don't perform well at high temperatures. There is, in fact, at the National High Magnetic Field Laboratory, an all superconducting magnet which makes some use of high temperature superconductors, principally for leads that go down from higher temperature down to 4 degrees. But the critical current increases dramatically as you reduce the temperature well below the transition temperature. So we don't have much prospect at this time to have all superconducting magnets which would function at, say, liquid nitrogen temperature.
But let me chime in and say that if we had a drive for that kind of research, because it was recognized as a demonstrated need by federal funding agencies, I think that there's some exciting developments that could maybe look for those performance metrics and look for the development of new materials that might be able to reach into that range and still reach those critical current densities. So let me just leave that comment out there as maybe a future prospect, a decade or more out.
Absolutely.
Yeah.
Great, thank you. That's really exciting to hear. We have another question. There are several people that are just kind of curious, and I don't know if this is something we'll be able to answer for them, but do you know if there was any sort of estimate of like the global availability of helium? This came from Mashal on Earth, and maybe how long they think this finite resource will last potentially?
Well, as we've discussed in this webinar, helium is really obtained parasitic to natural gas production. And natural gas production is a gigantic industry. Helium is a tiny part of that. I think the helium that is contained in the Earth will be there for a significant period of time. What's really at issue is, will the natural gas source, that which we're parasitic to in order to provide helium, will that be a steady source, and will it remain commercial to refine it to produce the helium that we need?
Well, let me chime in also. So that quick answer that we've seen in other literature that's hard to vet is we've heard that we have roughly a 200-year supply. And that sounds pretty comforting because 200 years sounds like a big window. But that's it, current consumption rates, let's say. And something to think about is the demand for helium, we've also heard, is going up 10% per year, roughly, worldwide. And that's in part driven by the semiconductor industry that's coming out of Asia. And in addition, let me just give you a couple of metrics that will be useful for your listeners, and I can provide a source for this after the call if needed. There are 13,000 MRI machines in the US. And while they're in a closed loop of helium, they each must be cooled down at the first charge with helium in order to operate. There are 50,000 MRI machines worldwide. And if all countries want more and more MRI machines, there's going to be this ongoing demand for helium to cool them down, even if they're in these closed cycle systems. So you can imagine that even though we are looking at a 200-year supply, we need to make sure that we preserve it as well as we can, because it's hard to imagine a world without, let's say, things like MRI machines for medical uses.
Thank you. We had a question from Stanislav. Is it possible to extract helium from the ground without removing the other byproducts, natural gas or oil, or do they come together?
Well, I think they're mixed intimately together. And the reason why the natural gas there in the first place to be mined is because it also has been trapped on a much shorter time scale, of course. They have been mixed together. And even in the National Helium Reserve, the helium which is in the reserve is only about 70% so-called raw helium, and the rest is natural gas. I don't see a way of separating it, but perhaps that's an idea that could be explored. I just don't myself have any information about how that might be done in situ.
Agreed. And not at the levels that we would need.
Thank you. We had a question from Darcy, who writes, for those with MRI or NMR magnets, especially multiple instruments, is there a widely accepted and really readily accessible standard operating procedure that ensures limited loss of helium during transfers?
I'm so glad Darcy asked. Thank you. I got that question just a few weeks ago at a PANIC NMR meeting. It's a practical applications of NMR conference. So indeed, we are preparing a couple of diagrams and some photos to show people how one can do that. So the answer is yes, we will find a way to get that resource out publicly. So thank you for that question. Indeed, there are methods to do so and SOPs.
Great, thank you. We had kind of a long-reaching question here. Is nuclear fusion a way to potentially make helium in the future? And I don't know if Professor Halperin or Professor Hayes wants to try and answer that. That's from Yang.
Well, that's an interesting question. It's well established that if we move to securing power successfully from fusion reaction in a tokamak, that there is the possibility of producing helium by that source. I was told by an expert in the field some years ago that that might even generate more helium in the atmosphere, which is of the light isotope, Helium III, not Helium IV. If that were true, then that might also be sequestered in the energy production from fission reactions. But we don't know where that energy source is going at this present time, how it will be developed, and whether it will be profitable.
Great, thank you. That's actually a really great segue. We've had several questions about Helium 3. Sean was wondering about the usages of Helium 3 versus Helium 4, and he was also curious about where Helium 3 comes from.
So Helium 3 is produced from the decay of tritium, which is heavy hydrogen, that is mass 3 hydrogen. Interestingly, the half-life of tritium is about 12.5 years. That's not the hundreds of millions of years for Helium 4. So in fact, we can make tritium, and we have done so in the weapons industry, and that is what has been the principal development that produces Helium 3. However, the amount of Helium 3 that is available by that source is relatively small. The current price for Helium 3 is between, say, $1,000 a liter to $2,000 or $3,000 a liter, and that's not a liter liquid. That's a liter of gas, STP. So probably not a good substitute for what we're talking about here, that is for cryogenic purposes.
Thank you, Dr. Halperin. We also had, again, going back to liquefaction questions, there's been several questions about do you have tips on how to arrange purchase of the helium that people collect, especially if they're collecting it as a gaseous form rather than going all the way back down to liquid. Do you have any tips on finding local purchasers?
So in our case, our specialty gas suppliers in the St. Louis area, and there's more than one of them, have shown an interest in taking essentially what is gaseous helium, but at low grade that has been boiling off of all of our instruments. And so usually those gas suppliers will work with you in order to set something up, in my own experience.
What about you, Professor Halperin? Have you had a similar experience?
I would say no. The amount of helium that we need to run a liquefier at Northwestern University is reasonably substantial, and there's a cost effectiveness to purchase it in bulk in liquid, and then it can be transferred immediately for use by the researchers at the university and then recovered. So there's a cost advantage to going that route, but it is a route which is followed by other institutions in which they buy gas rather than buy liquid initially. So I think Sophia has correctly answered how once it boils away at your institution, or you have it for some other reason, that you might want to be able to sell that back to providers of gas and therefore be more efficient.
Great, thank you very much for that answer. This is probably a bit too much of a crystal ball, but we had a question from David about what the expectation or outlook is for once the helium reserve is privatized in 2021. Do you know if people have had much discussion about what they foresee happening once that occurs?
Lots of discussion.
I don't think anyone knows. I think that's the truth. What you're seeing is a market that's out of equilibrium, and that's why we're having both price and supply issues in anticipation of 2021.
Just keep in mind that over many years, up till about 2 years or 3 years ago, that 30% of the world's supply of helium came from the US National Helium Reserve. And if that closes and becomes not available to researchers at least in the United States, that's going to be a tremendous shock on the market. And that, since that's going to take place in some form, which we don't know the exact structure of, in about a year and a half, it is a subject for a lot of discussion and worry.
Thank you. We have a question from Donald. He was curious about how much the use of helium as an inert carrier gas and gas chromatography impacts supply and demand, but it sounds like it's relatively small. Would you be able to comment a bit more on that, perhaps?
It's relatively small compared to those who use liquid helium, of course. And so it's still important to care for it, to attend to it. And nevertheless, I think it's the liquid helium users that are the bigger consumers, if you will.
One question here was about the Large Hadron Collider from Tim. He was curious if its large use, and he cites, I'm not sure if this is accurate, 120 tons of liquid helium is contributing to the shortage. Is the shortage really caused by large users overall, or is it more a function of the system, I guess?
Well, the LHC, as was correctly noted, the LHC has in the volume of helium which is required about 1 million liters of liquid helium, but it's a closed system, and that is quite accessible to discipline and reduction of the losses. So I think that the initial charge is gigantic, but that's not required to replace until there's an upgrade of part of the accelerator. So I think there are massive uses of liquid helium for accelerators which are being planned in the future, and that will be a major perturbation in the market at that time.
Thank you. Would you be willing to provide a little bit more background? We've had several questions about the closure or privatization of the Strategic Helium Reserve. Would either of you be able to give a little bit more detail about that?
There was legislation in 2013 which specified the details of what was expected by Congress for the privatization of the reserve. There are caveats in the writing of the legislation that federal use should be attended to, but not sufficiently specific that it gives confidence that when the reserve is being sold or privatized, that there will be a clear mechanism by which research, that is, federal use of helium, will be taken care of appropriately. And it's that concern that we've been talking about a little bit this afternoon. Nonetheless, that legislation is clear. The end of September 2021, it's required by Congress that the reserve be closed.
Thank you for that. I think we have time for maybe one more question here, and so I just want to highlight one from a high school, the Hansdale High School sophomores who wrote in, and they were curious if there has always been a limited supply of helium to begin with. I'm not sure if that means just on the planet or if it means in terms of users.
Well, it's telling that the US government decided to create a strategic helium reserve to begin with. So back when this was created, and Bill will get the date for me, I believe it was quite some time ago. But certainly putting that aside, that resource, I think everyone has been cognizant of this being valuable, and yet I don't believe it was in short supply, at least that I know of. But it's been used in airship and used to pressurize rocket engines when the rocket and missile program were being developed in the 1950s. The use in research, which is where it touches upon a number of scientists, really became much more common, I think, after the 1950s. So it's safe to say that we haven't experienced these kinds of supply shocks until roughly 2000 and onward. I think it's safe to say. But Bill, what do you think?
So the Helium Act in 1925 was passed by Congress to recognize the uses of helium and its federal exploitation. And that was followed by an amendment in 1960 that recognized further that it would be important for strategic interests to store the helium and that could be bought, and encourage providers who are mining natural gases to refine it and send it to the Bush Dome, which is a cliffside field near Amarillo, Texas. So that started the strategic allocation of helium in the National Helium Reserve around 1960. Following that, since about 1975, there has not been a net increase from purchasing by the federal government to increase the reserve. It's been held more or less at a constant level. But more recently, following 1996, with the Helium Privatization Act, then it was legislated that the helium that was in that reserve should be sold off. and that was done in auctions with the endpoint expected in 2021 of 3 billion cubic feet of helium raw gas. So that means that at some point there will have been significant reduction in the storage of helium that was done for strategic purposes, and the endpoint is, as I said, when finally the reserve is taken out of operation.
Thank you both for your excellent insights you provided today. If there's one important lesson for our listeners that they should remember from today's webinar, what is it?
Okay, let me go first. My feeling is that if you've been listening to this, you should get the impression that when you use liquid helium, please improve the efficiency with which you use it. It will reduce your costs and your vulnerabilities. And you might try joining with other users in order to recycle. Talk to your program managers in the federal government that support you and your members of Congress about your requirements in order to further those.
And from my perspective, it's certainly exciting news that there are new international supplies being identified, but I think we need to ask ourselves whether we can weather supply shortages that are tied to international sources when it's so critical for so many things that we do here in our research aims, but also domestically. In addition, let's look forward. Are there opportunities now, because we've defined this need, and this is a critical element, to invest in helium-free technologies, and can we think about redesign of our instruments? And I think that that's a great opportunity with the tremendous talent pool that we have looking into high-temperature superconductors and those for magnetic field generation. So I'm looking forward to things that we can do in the future.
Thank you for watching this presentation. ACS Webinars is provided as a service by the American Chemical Society as your professional source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.